everybody to another version of the Carolina Math Seminar. Our first speaker is Shannon Michaels. She's a student here at USC Sumter, and she's going to talk to us about a relation between Fibonacci numbers and Lucas numbers. I think it's worth to mention that the work that Shannon is going to present here, it was on a post problem on the journal, the Fibonacci Quarterly. She proved one of the identities, and she submitted that proof to the journal for publication. So she's going to talk to us about that.
Thank you to the organizers of this math seminar, and thank you for the opportunity to speak today. My name is Shannon Michaels, and I'm going to be discussing the relation between Fibonacci numbers and Lucas numbers. Leonardo Fibonacci was an Italian mathematician from the 12th century. He discovered a set of numbers whereby each integer is the sum of the previous two integers. So beginning with the set of Fibonacci numbers, they begin with 1, 1, 2, 3, 5, etc. Each Fibonacci number is assigned an F number, so F1 equals 1, F2 equals 1, F3 equals 2, etc. There is a recursive formula for Fibonacci numbers beginning with F1 equals 1, F2 equals 1. Fn then equals Fn minus 1 plus Fn minus 2. So the Fibonacci number is the sum of the previous two. For example, the number 8, the previous two integers are 3 and 5, which give you 8. There is a set of numbers, Lucas numbers, and they have their sequence beginning with 1, 3, 4, 7, etc. They follow the same basic principle. The Lucas numbers are assigned an L number, L1 equals 1, L2 equals 3, L3 equals 4, etc. And Lucas numbers have a recursive formula as well, similar to Fibonacci, beginning with L1 equals 1, L2 equals 3. Ln then equals Ln minus 1 plus Ln minus 2. So the basic principle applies with the Lucas numbers, the sum of the previous two. For example, the 11, the previous two integers are 4 plus 7. This is the primary relation between Fibonacci and Lucas numbers. The formula Ln equals Fn minus 1 plus Fn plus 1. Now if you take the Lucas number, the one highlighted in red, you begin with 1, 2, 3, 4, 5. That is your Lucas 5, L5. Adding the recursive formula into that, the Fibonacci numbers, if you take the 5 minus the 1, you get 1, 2, 3, 4. Take the 5 again, add 1, you get Fibonacci 1, 2, 3, 4, 5, 6. The sum of 3 and 8 give you the Lucas number 11. In the theorem that I submitted a proof to the Fibonacci Quarterly, I used these three identities in the proof, which I have wrote here for later. And this is the theorem that I submitted a proof for that's currently under review. I'm going to go ahead and prove this theorem by hand for you now. So I have my identities, and I have my theorem. I'm going to begin proving on the left side and getting it to look like the right side. So I'm going to begin with this side here. The law of exponents says that I can take these two terms and place them under one square. I have Fn plus 1, Fn minus 1. This is where I can substitute Cassini's formula. If I solve this for Fn plus 1, Fn minus 1, I can substitute here. I can expand this square by FOILing. can cancel the FN4s, and I can also factor out a -1 here and here. I have an FN squared here. This is where I can bring in my second identity, also incorporating Lucas numbers into the left side of the piano. I have an LN squared this time. I can bring in my third identity here. At this point, I can combine terms, the +2 and the -4. I'm going to move over to the other side. I'm going to distribute the 2 here. And here. At this point too, I can multiply top and bottom, the -1n. And I can go ahead and combine terms again. I have 2 fractions. Now it's getting there. It's starting to look like my right side. I'm going to go ahead and move the fraction divided by 5 over to the -1n. And now my left side looks like my right side, and I proved my theorem. Now you may be wondering, how does this apply to me? How do these Fibonacci numbers and Lucas numbers apply to me? Fibonacci numbers are found and applied in a bunch of different areas. They're found in science when discussing DNA parentage. They're found in architecture construction. They're also found in nature. For example, we have the center of a sunflower, and these blue dots represent the seed formation and the center of the sunflower. The formation of the seeds going this way, counterclockwise, represent the consecutive Fibonacci numbers. The formations that you see going this way actually represent a Fibonacci number. This reminds us that nature is organized and deliberate. I have a short video that I'm going to show, and it'll incorporate the idea between Fibonacci numbers and nature a little better.
Thank you.